Okay, then let's continue. So now that I reminded you briefly of integrals, we can talk about the actual content of today's session, which is the real Fourier series representation of a univariate real-valued function. And this real Fourier series representation applies to functions which are set to satisfy the Dirichlet conditions. And these Dirichlet conditions are these mathematically subtle conditions that ensure that such a representation actually exists. And one of them is continuity of the function. In general, these are a little bit too subtle for cognitive neuroscience, so we don't discuss them. One is not that subtle, so I couldn't really throw it out. So one thing that this function that for which we now want to compute this omega k, ak, and bk, what this function needs to satisfy is that it's periodic. So if this is our univariate function of interest, it needs to satisfy the so-called Dirichlet conditions. So if you really want to know what those are, of course there are some references also, and you can look into these references, what these Dirichlet conditions are. You will find that they are not horribly interesting, unless you like things like continuity of function, Stetigkeit. One of those, however, is that the function is periodic, which means that if you add a fixed constant t to x in the function, then you get fx again. Yeah. So picture-wise, this means that the function repeats itself every units of t. So if you have something like, if the function is maybe, I don't want to draw a sign. If the function is something like this, then, although this will not really work because this function is not continuous, but then it repeats itself here, and assuming that it somehow managed to go here without being non-continuous. So this is quite a strong, from my perspective, quite a strong condition, so that it's continuous. So I didn't want to throw that out. However, there is later, and I don't think I will be able to discuss this in terms of time, there is this section on periodic and protracted functions, which essentially shows that from a data analytical perspective, this condition of periodicity is also not that strong. So if one is in a data analytical context, it doesn't hurt that the data that you observe is typically non-periodic, right? So you have you observe a time series, and then you are not that lucky that every let's say 10 data points, this exactly same data comes up again. That usually never happens. So your data and function that you're interested in usually won't be periodic. However, it's one of these Dirichlet conditions, and it's actually also required for the derivation. So that said, all other mathematical subtleties are left out. So if this function satisfies the Dirichlet conditions, then actually this Fourier series representation of fx exists. So this thing actually is meaningful. And yeah, for all, so that's also how we can write for all x in the domain of the function. And we thus far we already were, but we weren't really sure whether it exists, and now I'm telling you it exists. the more important thing is now that we get formulas for the omega k, ak, and bk, and they take the following form. So omega k is k divided by t. And yeah, this is, I think, the main reason why I couldn't throw away the periodicity of the function, because the frequencies themselves are defined in terms of the period of the function. So if I wouldn't say that the function is periodic with period t, this t wouldn't be there. So we need this t. So the omega k are defined by k divided by t. So think about t is something like 3. Then the omega 0 is 0. The omega 1 is 1 divided by 3. The omega 2 is 2 divided by 3, and so on. The cosine coefficients are given by a0 1 over t. So again, that's why I need this t. And then an integral, surprise, surprise, because that's why we talked about it, of the function fx over the integral minus t half to t half. And so that's only a 0. The remaining ones for k, 1, 2, 3, and so on are given by these integrals. Fx cos 2 pi k t x dx, and this now for k 1, 2, 3, and so on. And finally the bk, the b0 we can actually set to 0 as shown below, and bk is fairly similar to ak, but maybe not that surprising then with a sine function. Oops. Simply sine x. So of course I could also have written omega k in here. Doesn't matter. So the important point about these formulas is the following. If we are given this function and we now want to compute the omega k, the ak, and the bk, these formulas tell us exactly what to do. So the omega k here tell us, okay, you need to keep the k in mind. So k goes from 0, 1 to infinity. And the omega, so let's say the 10th, if k is 10, you get that by dividing 10 by the period of the function. Then we have clarified the omega k. And then, of course, we also need the ak to have our defined generalized cosine term. And for this, it tells us, okay, if k is 0, so if we are having a0, we need to compute the integral of the function fx over the interval minus t half, t again the period of the function t, which we are also given up to t half. And for the remaining ones, we have to compute the integral of the function multiplied by this cosine cosine term essentially, or a little bit generalized cosine term, where we here have the circular frequency kt. We have to compute this integral, and then the same for the sine coefficients. b0 we can set to 0, and bk we need to compute integrals fx times the sine function with the circular frequency kt. Yeah. So essentially the answer is to compute the omega k, we don't need to compute much. We just have to divide the k by t, and for the coefficients we need to evaluate integrals. Yeah, and as we learned last hour how to evaluate integrals, we can now go and evaluate all these integrals. Of course, that's it's an analytical challenge, if you want. So because first of all, there are many cases. For simple examples, of course, after a certain number of k, the remaining coefficients, one can show that they are zero. So usually one doesn't have an infinity of coefficients, but a finite number of coefficients that one needs to compute, at least in these well-behaved examples. And then, yes, one has to have this function fx, for example, 2x plus 1, multiply it, in this case, with this cosine function, get a new function that is then the multiple, and then compute an integral performing the antiderivative and evaluating then the basic fundamental theorem of calculus. So take the antiderivative at the upper boundary minus the antiderivative at the lower boundary, and then, and this also keep that in mind, these fancy formulas here, these are numbers, right? So if you do this for a defined t, so if t is, I don't know, 10 and k is 20, you have a form of the function, then what you get out here is a number. Because it's an integral, it's a definite integral, you might get out something like 7.3 or something. Yeah. So although it might look a little bit complicated, these are just numbers. So the a, k, b, k, and a0 and b0. Yeah. Questions?
You have a function like 2 times x plus 1. What is, so the t is 0, right?
Oh, that's a good point. Yeah, so it doesn't.
Because then you can compute.
Yeah, that's a good point. So that was maybe not the best example. So you need to have a So you need to have a function with a period. So that was not a good example. So maybe you can. The cosine function is a function that has a period. So if you want to compute this, then of course it will be boring. So you need to find functions which are kind of periodic. So one can, of course, define functions that are periodic and continuous by making sure that when they start repeating themselves, they are again at the same point. So that there are no discontinuities in the sense that you have to leave with your pencil the paper when you doing the switch. But yeah, so this is why also this thing with the periodicity is somewhat of a harsh criterion. However, it works because of this. One can use these protracted functions as well. The thing is, we actually don't want to compute much with those, so we don't do examples of those. We rather would like to get familiar with these kind of terms, that these coefficients have this form. So this is where we're getting at, because in the end, when we're dealing with data, of course, integrals are replaced with sums, and then we can actually evaluate these coefficients based on sums. But we are getting there, so it takes a little bit of time. Yeah?
The function we are using to compute the AK and DK is not the function up there, right? So
no, it is.
It is?
Yeah, that's the crucial thing. So so this is exactly this function. So this is then how one can solve this task. So if I give you this function f, which I say is periodic with period t, so it's not 2x plus 1, but something else, then you know now this formula. And because you know the function f, you can compute this.
Yeah, but we don't use the sum of AK cosine, like the longer.
Okay, yeah, okay. So the thing is, yeah, okay. So this is what. Okay, so what I'm actually trying to do here is that you have a function fx, and the problem is that I'm not telling you what this function, how this actually looks. So maybe I need to be a little bit creative and think of some kind of function that is periodic. And I don't want to use cos. Can I use cos? Well, it's a little bit boring with cos, because then it's relatively clear how this looks. Do we have any example here? What do we have here?
So, but basically we are computing AK, BK, and omega.
So wait a second. So let's say, believe me without checking it, that for some weird reason, this function here is periodic. No, it's not periodic, but I guess. But believe me that this is periodic, and we could do that. Then the thing is that I'm telling you the function is exponential minus 2 divided by x squared, and you now have these formulas to compute this Fourier series representation of it, so that you actually express all of these values, express them with these cosine and sine.
In that generalized form.
In this form, where you can compute based on this definition of the function fx, you can compute the ak, the bk, and the omega k. Yeah, that's.
First, we use the other formula to compute AK, BK, omega,
Mm-hmm.
and then we put all that into the first.
Exactly. Yeah. Into this form. So this is why I'm calling it the Fourier series representation. So the function itself is something like this, and it can be represented in a different way, right? So it can be represented by the sum of cosine and sine function, and this, of course, is inspired by the general idea that we have some function in the time domain, and we want to, in the end, get to a representation of this in the frequency domain. And then the question is, of course, what is the amplitudes of these different frequencies? Let's call them omega k for now. And here, in a way, not really, so you need to be a little bit patient there, but in a way you already see some amplitudes for frequencies. You see an AK and a BK as a multiple of a cosine with a certain frequency. Yeah. But it's so the task goes via a function that is defined like this. The thing is, in the end, what we want to get it is, of course, that we don't have like an analytical form of this function, but we just have some data points, which are kind of a discrete representation of a function. And then we can still do the same thing like this, but with sums, and then we can do what everybody does in cognitive neuroscience to look at gamma oscillations in consciousness. But only if we understand all these formulas, then you're allowed to look at consciousness. If you don't understand these formulas, you're not allowed to talk about consciousness. Really, I'm serious. With gamma oscillations. If you talk about consciousness in some other context, then it's fine, but not with oscillations. Other questions? But no, because the question is, of course, why, that's this is also in a way here a little bit kind of the mathematical approach chosen. So I put this whole thing in the script. I put it into a frame like this, which should signify something like a theorem or result. In school, maybe in German high school, it was always Satz. Yeah. Then the teachers said Satz. And then they said something horrible trivial, something like, I don't know, a plus a quadrat plus b quadrat c quadrat. It's not trivial, but it was always Satz. And then the mathematical thing is to first establish this result or the theorem, and then to show that why this actually holds. So that's different from a lot of mathematical writing that you see in more applied literatures, which go, let's start with something and compute a little bit here and there, and in the end we have a result, and then we can go home. In math, the result is given up front, and then one should ask why. This actually results a little bit from the history of math, that things are often used in the applied sciences, and then at one point some mathematicians ask actually why does this actually work, and this is then how proofs are usually established later than things that have been conjured, I guess, previously. Good. So the question is then why, where these formulas come from, why it looks like that. And this is this proof of 511 and 512 in the script. And what this proof essentially does is to put the question of why this works to a different level, because it says it holds because there are the so-called orthogonality properties of sine and cosine products. And to briefly, or not briefly, but to sketch now why these formulas, how these formulas come about. They come about because the sine and cosine satisfy so-called orthogonality properties. And the thing is, we will not prove that they hold, so we just put the question of why this whole thing works to a different level. However, one can, in a way, appreciate these orthogonality properties quite readily visually. So the orthogonality properties for the cosine and sine are the following things that I'm just writing up. So if you have a cosine of circular frequency kt and you have a cosine of circular frequency jt, and you multiply them, and then you integrate the result of this multiplication from minus t half to t half, where t is now just a number, you get the following. You get 0 if the k doesn't equal the j, and you get t half if the k equals the j and both of them are not 0. So, or one of them is not 0, so the other is also not 0. So whenever you have, what this means is that whenever you have two cosines of different circular frequency, this integral actually comes out 0. If you have them of the same frequency, it comes out t half. If you're a little bit familiar with dot products, which some of you I guess are, so dot products of vectors and orthogonality, this is of course the same intuition. So in terms of orthogonality, that if you have like, I don't know, a 3-dimensional vector 1, 0, 0, and you multiply it with another vector 0, 1, 0, then when you form the dot product, you get 0. And so because they in a way are orthogonal, and if they are the same, so if they are 1, 0, 0 and 1, 0, 0, then you don't get 0. So the people with some linear algebra, they know what I mean. This is the same thing here, only for functions, and for the sine function in particular, and the cosine. The same thing holds essentially for the sine function. So in terms of if they have the same circular frequency, they are not 0. This integral is not 0, otherwise it is 0. And then finally, if you multiply a sine and a cosine, regardless of whether they have the same frequency or different frequencies, oops, there's an x missing, I tend to forget the x, you always get 0. So, of course, these would need to be proven if you use them now, or we use them to show how these coefficients come about. Instead of proving them, I plotted them. So here you see a sine function with two different frequencies. used here radial frequency instead of circular frequency. So you have sine x and sine 2x, and then you see that there is one repeat for the blue over the interval of 2 pi, or 2 repeats for the red. Yeah, so the red has 2 repeats. Can one see the colors? Not really. But you see that there's one sine that has a lower frequency and the other one that has a higher frequency. And then I plotted the product of them. So this is now the thing where you have this gray between the x and the function. So if you do the product, you get this third function here. And then I kind of made grayish the area between the x-axis and the function. And if you look at it with a little bit of fantasy, you see that this and this and this and this, they cancel each other out, so you get 0 for the integral. However, if you have two sine functions of the same frequency, so for example, you have k and j being 1, so you essentially compute the square of the sine, then of course what that means, if you compute the square, that also the negative parts of the sine become positive. If you compute the integral, you don't have like a positive part and a negative that cancel each other out, but you have only the positive, and then of course the integral is not 0, but is t, what is t here? I guess it's 2 pi, yeah, so it's not 0. And then finally, if you multiply a sine and a cosine, again, so you have a sine and a cosine of different frequency, then again, if you look at this function where the gray is, then again you can imagine that things cancel each other out. And this is shown here, so this is kind of making visually plausible in a number of cases, also for cosine here, that these orthogonality properties hold. It's not a proof, but it looks like that. If you plot them, it looks like this could be true. Yeah? And of course there is a proof which you can go over in your own time. Good. So these we now need to compute the coefficients, and this will be then the last thing. But keep in mind that now that when I show you now how to compute the coefficient, and I'm using these, I haven't really proven those orthogonality properties. So you can say, well, it's not really a proof, is it? But then this is kind of the infinite regress that you can have in math. And you also need at one point to stop and say, it's well known that the sine and cosine fulfill certain orthogonality properties. And then you don't have to prove it. So, okay, so how are these things that I just established now related to computing the cosine and sine coefficient? That works as follows. So what we actually do is, as also proposed here, we actually now set our function fx equal to our generalized cosine, our Fourier representation series. So in this case, here again we have our magically periodic function that looks like this. And on the right side of the equation, we now put our Fourier representation, Fourier series representation, and we set omega k to, to k. Sometimes that's the wrong point. To So we set our omega to kt as by the theorem for the real Fourier series representation. So we take this as a given, So we already plugged that in. You actually, I see that a lot of you are writing down what I'm trying to write down here. You don't have to do that because it's all in the script, right? And it might be easier sometimes to, especially given my handwriting, to focus what is on the script, but it's of course up to you. This is all in the script, so you don't have to actually write it down. So now if we want to compute the AK, we somehow of course need to solve for these AK and do something, and we want to see that these AK formulas are the ones that I have shown you. So to do that, what one can do, and this is now the magic of proving things, is to multiply both sides by a cosine of circular frequency jt, so that one actually gets fx cosine 2 pi jtx, and on the other side, well, I'm writing this down, but then I don't write down the other next step, gets this ak cos 2p kt. Could say I'm a cosplayer. So the only thing that happened is right now that I multiplied both sides of this equation by this cos 2 pi jt, which shows up here, and shows up here. Then the next thing that we can do to get to our AK is to integrate both sides of the equation from minus t half to t half, where t is again the period of our function f. And maybe you already see where this is getting at in terms of the orthogonality properties. Of course, we need to, if we put an integral, it should put dx here and a dx here. And then one can, under certain conditions that mathematicians study, can interchange the formation of an infinite sum and an integral. Does any one of the math kids remember a theorem that says that you can do that? There is one, but I also don't remember the name right now. There are these what's it called?
I don't know. I just know that I once put it on an exercise sheet and then he said you have to prove this.
Yeah, in general, one actually has to show that this actually is allowed, because this, but there is a mathematical theorem that says that this is possible for quite a broad range of conditions, but I also don't remember the name right now. In any case, so this, what I'm doing here right now, this is not trivial, but I'm doing it nevertheless. And at the same time, I'm using this linearity property. So I'm splitting up this one big integral, which we had just a second ago, and splitting this up into two integrals. So there's a dx now here, and then there's another integral starting here. To t half dx, and this hazard dx. So we have, what we now have is an integral on the left side of the equation, and then a sum here, and in the sum we have an integral of this form and an integral of this form. And then, of course, we are quite close to what we actually had above in terms of the sine and cosine orthogonalities. And this is what we will actually use in a second. So we know, for example, for the cosine, that if they don't have the same circular frequency, then these integrals are zero. Now we have to think again what happens here. This j was arbitrarily chosen, and this k runs from 0 to infinity. Yeah? So j is, for example, 10. Now, then the k here, this k in the kt, runs from 0 to infinity. Whenever it's not 10, this integral comes out 0. However, if the integral if the integral comes out if k comes out j, then this integral is not zero. Yeah, so think that k is running from 0 to infinity, j is some given thing. At one point, k will be the same as j. Then this integral is something. Otherwise, it's always zero. So most of the time that k takes on a given number, this integral is zero. Here we have here it's even simpler. Here we have a product of a sine and a cosine, and whatever k and j, whether they are the same or different, this is always zero. This is what this other, what this last sine cosine orthogonality property says. So here, this is always zero, so we can actually get rid of it. Note that we also get rid of the bk in this case, so we cannot actually solve for our bk's, but this is also not what we want to do. We're working on the a case right now. And then we have to think still what's happening here. So if these are all only equal if k equals 10 and the other ones are 0, then we get also rid of this sum sign. So we get actually aj, because only when k equals j, this is not 0, and we get out our t half minus t half cos 2 pi j, because only if k is j, this is not 0, cos 2 pi jt, this was always j. And on the left hand, we still have this. Maybe I'll write it up a little bit nicer. At least I'm trying. Almost. And now we see that we kind of have our aj isolated. Of course, the aj depends on the j that we choose. And now we can again use the orthogonality properties of cosine and sine, which said that for a cosine of the same circular frequency, the integral is actually t half. So what we get is aj t half. And then we essentially just need to put the t half on the other side and get aj equals 2t fx cos 2 pi j t x dx. And now the j that we chose in the very beginning was of course arbitrary, and we can choose anything, and we can also rename the whole thing. So look, that what we did here is that we multiplied with the circular frequency omega j jt. Of course, we could do this for any j, and we could also call j k. Then we would need to call our, it's just a running index here, we would need to call that I or something, and then the formula, instead of coming out with a J, it would come out with a K, and we can just do it. So we have for our circular frequency omega K, we get this, and then the last thing is to think about what happens if K is 0. So our case, the coefficients for circular frequencies that we're interested in run from 0, 1, 2, and so on. And if K is 0, then this just one X. So we have 520. Okay. Yeah. If in the case that we have 0, of course we don't want to. If we it also works with this. I'm actually confusing myself here. So if we have 0, we can, I'm doing it a little different now in the script. If we have 0, we can of course put 0 in here. Then this is 1, and we have AK. Am I confusing? I'm confusing. What am I confusing? AT. Yeah. No. That's a little bit confusing in the script because I'm going back to one step up, but one can actually just read it off here. So if K is 0, then this is 1, and our A0 is 2 T. Yeah, read. Somehow I'm confused about this last step. Should have prepared that. So there it's AJ. So divided by T half, we obtain this. That's fine. So we have all of them except for the 0 one. Now I'm saying it's this. T half. There's one. Never mind. So think what the problem is right now. I have solved it for an infinity of values. Yeah, from K1 to infinity. I've solved the whole thing. And what I'm wondering right about is the one thing, namely the 0, where I'm just confused. So think if you kind of evaluate what I'm doing here. He's done it for an infinity amount of values, so for all of them, and it's just one thing that he's confused. So just take this into your thing. So for some reason that I can't trace right now from the quite clearly from the script, is that for A0 we get this. It's fairly straightforward. I'm just wondering where my, so this is 0, this is 1, but then it looks if the 2t is still there, so I'm a little bit worried about this 2 versus the 1 here. But that's a really minor thing, so don't worry about it. Maybe next time I have cleared up on that and give you the idea, but you have the whole thing written down there. So we've now solved the thing for the AK coefficients. So basically I've shown you where they come from, why they take on this form they take on, right? So this doesn't come out of nowhere. So this comes about because this sine cosine orthogonality properties hold. Yeah. What we haven't shown is where these BKs come from. This is also written up in the script. So the different approach there is to not in the beginning start with the cosine, but to start with the sine. Then you get here in the first thing, in the first term, you get the cosine times sine thing, which is 0, and then you end up with the BK coefficients. In the end, as we ended up here with the J or AK coefficients, and then finally one also sees that the B0 one can fix as one wants to. But so this is something you should go over yourself, kind of in retracing what we actually did here and understanding what this was about. But this is, so these formulas that I put out here, they basically go back and derive from the sine and cosine orthogonality properties. Yeah? And this is why one can solve them. I mean, it's a little bit, so I find it, when I first encountered this, it's quite surprising. So that you have a function that is defined in a certain way, and then you can represent this function using really sine and cosine functions, and you can analytically compute the amplitudes, and once you defined the circular frequencies. So I think this is quite amazing, but depends on how you think about it. Okay, and then, so this is the result, and what I've shown you in the last thing with writing a lot down, this is actually the proof, and again, to emphasize, it rests on the sine and cosine orthogonality properties. Yeah? Questions right now? The importance, so you always should, in math, you should always dissociate two things, the result and the proof. And from my perspective, it makes sense to memorize results, because this is mathematical knowledge, and this is really helpful. Because now if you memorize these formulas for the coefficients, you could in principle go and compute this. The other thing is the proof. For the proof, for proofs, I think it's in general important that you know the main trick, but you don't have to memorize the entire proof, because that would also be annoying. But if you have if you memorize, okay, it just works because of the sine and the cosine orthogonalities, then you have the essence of the proof already memorized. Yeah, but try to distinguish between what is more important and what are details. And proofs are, of course, for mathematicians, they are the most important thing, and this is where the work goes. From an applied perspective, the results are actually much more interesting. But if you, and then I'm usually using proofs mainly to understand the results a little bit better, because if somebody tells me, yeah, okay, these are the formulas, then maybe that worked in school where the teacher said, these are the formulas, and then you said, okay, that's how things are. But now you're grown up and you should always ask why. And then you are led to the proof. Yeah. So this is essentially what I wanted to do with the real series representation of the real Fourier series representation of a function. So I think based on this and knowing how to evaluate the coefficients and the circular frequencies on that, next time is then a good time to talk about the complex representation. Why do we talk about the complex representation? Again, because if you use FFT and MATLAB, or you use any kind of Fourier algorithm, you will come across complex numbers and complex exponentials, and you have to be able to make sense of those. Yeah? Good. Then, if there are no questions right now, let's stop here and start at 10 again with new cognitive methods.